Before we begin, let's define what a logarithmic equation is. A logarithmic equation is any equation where we have a logarithm of a variable. So it could be something as simple as log base 10 of x is equal to 5, or it could contain more complicated logarithmic expressions like the following. In either way, what we're looking for is our logarithm to have an inside portion that contains the variable. Similar to what we had in the last lesson, we want to develop a procedure to solve logarithmic equations. Now, the first thing that we want to do is if we do happen to have multiple logarithmic terms that all contain the same base, we want to combine them using the laws of logarithms. Once we have only one logarithmic expression, we can isolate that on one side of our equal sign. Remember that the action of taking an exponent to a particular base followed by taking the logarithm of that same base, those actions undo each other. So the idea here is to write each side of our equation as a power of the same base as the logarithm. Number 3 might sound a little confusing, so I'll show you through some examples here coming up. Then we're going to solve for whatever variable happens to be in our equation. Now, make sure that you absolutely check your answers. So certain values of x, we may not be able to use them in our original logarithmic equation because logarithms can't be negative. We ran into that problem in the very last example of the last lesson. So let's get to it. Let's begin by solving the following two equations. I'm going to start on the left with log base 10 of x minus 3 equals to 5. Our first goal, if we have only one logarithmic expression, is to isolate that on one side of our equal sign. So our first step here is to remove the negative 3 from the left side by adding 3 to both sides. So if we add 3, we should get log base 10 of x is equal to 8. Now that the logarithm is by itself on the left-hand side, we look to the base of our logarithm. In this case, it is base 10. So because it's base 10, what we can do is we can raise both sides of our equation and use 10 as a base. So here we'll get 10 to the log base 10 of x equals 10 to the 8. And what we've done over on the left-hand side is now we have an exponential expression that's base 10. We have a base 10 inside of our logarithm, so those two actions undo each other and we're left with the inside portion of our logarithm, which is x. So our final answer over on the left-hand side is x equals 10 to the 8. Next, let's take a look at 7 times the natural logarithm of negative 2x equals to 14. What we want to do in this case to isolate the natural logarithm by itself is to divide both sides by 7. When we divide both sides by 7, we get the natural logarithm of negative 2x is equal to 2. Now, since the natural logarithm has base e, that implies if we take e to the ln of negative 2x, this should be equal to e squared. So these two actions over on the left-hand side are going to undo each other, and we're going to be left with just the inside of our natural logarithm, which is negative 2x. And our right-hand side stays as e squared. Now finally, to solve for x, we could divide both sides by negative 2. So our final answer here is negative e squared divided by 2. In our second equation, we're going to have to use laws of logarithms in order to solve this equation. So here we have log base 10 of x plus 2 plus log base 10 of x minus 1 is equal to the number 1. Now, since both of these logarithms have the same base, what we can do is we can use the laws or the properties that we saw in lesson 5. So here, addition on the outside is going to become multiplication on the inside. So we can rewrite this as log base 10 of x plus 2 times x minus 1. Expanding through the brackets on the inside of our logarithm, we get x squared minus x plus 2x minus 2. And simplifying this one step, we're going to get log base 10 of x squared plus x minus 2. So in order to remove our logarithm, we're going to get the following. We're going to have 10 to the log base 10 of x squared plus x minus 2 is equal to 10 to the power of 1. Since the base of our exponential expression and the base of our logarithm are the same on the left-hand side, we are going to be left with x squared plus x minus 2 is equal to 10. Subtracting 10 from both sides, we're going to get x squared plus x minus 12 is equal to 0. And from here we can factor this quadratic expression. So we look for two values that multiply to negative 12 and add to 1. Those are going to be 4 and 3. And we need positive 4 and negative 3. This leads us to two possible solutions. Either x plus 4 is equal to 0, which gives us x is negative 4, or x minus 3 is equal to 0, which gives us x is equal to 3. However, when we substitute these values back into our original equation, 3 is okay. We get log 5 and log 2, which are both acceptable. But when we try to put negative 4 back in, we get log of negative 2 and log of negative 5, which are not acceptable. So we're going to have to get rid of negative 4 as a possible solution because it creates logarithms that are negative. So in this case, we're forced to conclude that x equals 3 is the only possible solution to our original equation. In our last example, we're going to solve the equation natural logarithm of the natural logarithm of x is equal to e. Now let's work from the outside in. I want to get rid of this natural logarithm, so I'm going to take both sides and I'm going to write them as the power of the base e. Like so. The action of doing that is going to remove this outermost natural logarithm. And we're going to be left with, on the left-hand side, the natural logarithm of x. Alright, we have one more natural logarithm to remove, so this suggests that we should take the base e one more time, like so. And the action of doing that is going to remove both the base e and our natural logarithm, and we're going to be left with just x over on the left-hand side. So a bit of an odd example here, we get x is e to the power of e to the power of e. Alright, my little epsilons, stay positive.